Section 3.5 Descriptive measures for populations and using the samples. So let's recall from before that n, small n, is always the sample size. Like means how many observations in the sample, how many entries, how many numbers. And we're going to use capital N for the population size. Also recall x bar was the mean or the sample mean, which we find the sum of all the numbers divided by n, sample mean. And here we're going to define mu. Mu is a Greek letter mu, is the sum of all the values divided by the population size. So that's population mean. Population mean. Another thing we learned before, small s, which is the sample standard deviation. And this was the formula for this was the square root of the sum xi minus x bar squared divided by n minus 1. And here we introduce a new variable. It's a Greek letter sigma, small sigma. So this is sigma, but capital letter, that one. But this one is small letter sigma. And this is given by, this is going to give us the population standard deviation. And what's the formula for it? It's written somewhere here. Population standard deviation. It's the same process exactly like the other one. It's just there's a mu here. The mu is the population mean, and capital N instead of small n minus 1. The other formula had small n minus 1. See, small n minus 1. Note, before we forget, if we take s and square it, if you square it, that will take care of the square root. This is called sample variance. If you do this one and you square it, population variance. Population variance. So the question is how to calculate this first. How do we calculate such a thing? And before we calculate this, there's another formula some people use. You can use this formula or the one that I highlighted earlier. Either one works the same thing. Let's try just to practice by hand. Find sigma, the population standard deviation, for the data 82, 77, 90, 71, 62, 68, 74, 84, 94, and 88. Okay, so the first thing we need to do is find the mean. And to find the mean, how do you find specifically the population mean? Is we add all these numbers up that you see, all the way until the last one, divided by how many numbers we are given. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 numbers. And if we add these up, that gives us 790 over 1079. That's the mean. We do need the mean or the population mean. And then I'm going to use a table to really find what this is with the formula. So here we write down the xi. These are the 10 values that we have. The x value is 82, 77, 90, 71, 62, 68, 74, 84, 94, and 88. These are the x values. Here we always write down the mean or the population mean, 79 for each one of them. And then if you look in the formula, it says xi minus mu. So we're going to subtract them. So 82 minus 79, that's a 3. This is negative 2. This is 11, negative 8, negative 17, negative 11, negative 5, 5, 15, and 9. And then I'm going to square each one of them. When we square 3, you get 9, 4, 121, 64, 17 squared, 289, 121, 25, 25, 225, and 81. And then I'm going to add them up. The sigma means add all these numbers up in this last column that I just found, and that gives me 964. So remember, I'm trying to find the population standard deviation, which is square root of the sum of xi minus mu square, all divided by capital N. And this gives me the square root of this stuff I just found. This is the square root of 964. And N, we had 10 of them, 10 copies or 10 numbers or observations. So that gives me 96.4. If you divide, so you divide these together on the calculator, and then we take the square root of this. Okay, so if you just put on the calculator, put 96.4, the square root of that, it will be about 9.82. If you don't take this, if you don't take the square root, that's not completely done. You must take the square root and find the exact value here for the population standard deviation. So this is important to know. And after this example, we can introduce two definitions that are written here. A parameter is a descriptive measure for a population. It's a descriptive measure of population. And statistics, descriptive measure for the sample. So in summary, parameter goes with population, statistics goes with the sample. Anything we work with goes like in the same way. So for example, if we average, let's say if we average means the mean. If we average all the students in statistics class, which would be considered our population, then the average is parameter. If we do it for a simple sample, simple random sampling of like 5 people from all the classes, then that's called that's called statistic. Not statistics. There's no s at the end, just statistic. And now other examples here we can introduce is the mu, the mean, that's a population mean, and this is the population standard deviation. Those are parameter. And if we take s, the sample standard deviation, or x bar, which is the sample mean, That's called statistic. Now we introduce sometimes these variables, the x values that we get, what we can do, we can standardize them. And how do we standardize them? We standardize them by introducing a new variable called z. So if we read here, the standardized variable. So z is defined as x, that's the value of the observation, any random observation given, minus population mean divided by the population standard deviation. So this formula is important, and this, whatever you get for z value, that z value will be the standardized version of x, of the x value. And this standard value always, the z, it always has a mean of 0 and standard deviation of 1. So if you're given a data and you run through the whole data and find the z-score for each one of them, then find the mean and the standard deviation for the z values. Their mean will be 0 and the standard deviation will always be 1. So let me scroll down and look at this example. Given the numbers 3, 5, -1, 3, 3, 5, let's say this, and we would like to determine the standardized version of 5, of number 5. So remember, to get that out, so what we need to find the z. It's x minus mu over standard deviation. Do I have x? Yes, this is x. X is 5. Do I have the mean? No. Do I have the standard deviation? No. We need to find them. So the mean is basically add all these numbers up, plus -1, plus 3, plus 3, plus 5, and we have 6 of them. That gives me 3. That's the mean. So I found the x and the mean. We need to find the standard deviation. So how do you find the standard deviation? As we did in the previous example, put all the xi values and then the mean, and then xi minus the mean, and then we square them, xi minus the mean square. So what goes in here? 3, 5, -1, 3, 3, 5. The mean is 3. If you subtract them, you get 0, 2, -4, 0, 0, 2. If you square them, 0, 4, 16, 0, 0, 4. What would be the sum? xi minus mu square. You get 20, 24. And n here, we got 6 of them. So then the standard deviation using the formula, sum xi minus mu square all over n equals 24 over 6, which is 4, square root of 4, and that gives us 2. So now we can go back up and say z equals, x was 5, mu, the mean was 3, standard deviation was 2. So what do we get here? Z equals 1. How about the same one? How about we need to standardize? How about for x equals 3? What do we get? What is the z? So z would be x minus, again, mu over standard deviation. X is 3 given, and mean we found 3, and this was 2. So we get 3 minus 3, 0 over 2, which is 0. That's the z value. How about z equals -1? Sorry, x equals -1. We need to find the z value. The z value is x minus mu over standard deviation. X is 3 minus -1. I'm switching numbers now. negative 1 minus 3 over 2, that's a negative 4 over 2, and that's a negative 2. So notice what I did. We got one of the first value that I got was 1, next one 0, next one negative. So what does the z, standardized z tells us? Just so you know, some people we call it the z-score. What does the z tell us, or the z-score tell us? So now let's note that the z-score, that's the same thing as these z values we got. We call them the z-score. Tells us how many, this is important, how many standard deviations the number x that they give us is above or below the mean. So if we go back to this tells us, this answer here tells us that x equals 5 is 1 standard deviation above the mean. This is at the mean, no standard deviation, 0. This 2 standard deviations below the mean, below the mean. So this is how you interpret this. Well, that's just another note. It doesn't have to be always an integer. So as another note, z could be, let's say 0.72 for example. So it means that the x value is 0.272 standard deviation either below or above. Like in this case it's a positive, so above the mean. So it doesn't have to be exactly an integer. It could be decimals as well. So other quick example here. Let's say someone or the mean on a math test is 85 for the whole class, and the standard deviation was 2. And let's say someone scores 86%. Okay, so what do we need to do here? We are going to standardize his grade, the 86%. So we find the z-score. Z is x minus mu over the standard deviation. X is this is the x value, 86. Mean is 85. Standard deviation 2. So that's 1/2. This means the student's grade was half of a standard deviation above the mean. What about if someone else got the same thing? Mean is same mean and standard deviation the same, but the score is 79, let's say. So now x is 75. We find z, x minus 85 divided by 2. That gives us negative 6 over 2 is negative 3. So 3 standard deviations below the mean. 3 standard deviation below the mean. That's what this is about. How we standardize scores and get it to be in standardized form. And we need this for later sections. You will learn more in depth about it later on, how we use it, what do we use it for. That's what this section is about.